Hi there, welcome to my channel. In this video, I'm going to discuss about the solution for finding square root of a given number. Let's look at the problem description. We are given a non-negative integer x and we have to return the square root of that number x, which is rounded to the nearest integer. Okay, and the return value should be non-negative. And also we should not use any built-in exponent function or operator to solve this problem. Let's take a look at the example 1. So the input number is 4, square root of 4 is 2. In the example 2, input number is 8 and the square root of 8 is rounded to integer, so it is 2. Okay. So the constraint for this problem are the value of x is ranging from 0 to 2 to the power 31 minus 1. Let's look at the approach to solve this problem. The input number given is 9 and the square root of 9 is 3. Okay. The brute force approach is compute the square of each number in the whole numbers and check whether it is greater than or equal to n. For example, for this case, starting from 0, 0 square is less than 9 and 1 square is less than 9, 2 square is less than 9, 3 square is greater than or equal to 9. So we return 3 as the output. So the time complexity of this is order of n. And another approach to solve this problem is using recursion. Basically, we can derive the square root of a given number based on a number that is smaller than n. For example, square root of n is equal to 2 times square root of n by 4. So when we expand this, so this 2 and the square root of 4 will get cancelled. Then we get square root of n. Okay. So basically we are writing a recurrence equation in which square root of n is defined in terms of the square root of a number that is 1/4 of current number n. Okay. So using this recurrence relation, we can write a recursive function and compute the square root of n. So the base case for this is square root of 0 is 0 and square root of 1 is 1. We recursively call a function to compute the square root of n until we reach the base cases and then we return. Okay, and we can perform the n divided by 4 by right shifting n by 2 times. Okay, similarly, if we want to multiply n by 2, then we have to left shift the number n once. So whenever a recursive call returns the square root value, we need to check one more case. There is a possibility that the next number of the square root may also be the actual square root of the original input. Okay, so to make sure we are returning the largest integers whose square is equal to the input number, we have to just increment the return value and check whether the square of that return value is equal to the input number. So in that case, we have to return the incremented value of the square root. So that's what I have written here. In the my square root function, first we check whether the number is less than 2. In that case, we return the number as it is as the square root of the number. That is for the base case, the 0 and 1. Then we make a recursive call to my square root function after right shifting the number twice. And then we assign the return value to the variable square root. Then we left shift the square root once to perform this multiplication with 2. Then we initialize the next integer square root with the value square root plus 1. We initialize the next integer square root with square root plus 1. And then we check whether the square of this next integer square root is less than or equal to the input number. In that case, we return this as the square root of the input number. Otherwise, we return Sqrt variable value as the square root of the input number. Let's look at the flow chart. The input for this procedure is number. First we initialize the square root variable to 0. Then we check whether the input number is less than 2 to handle a base case. If it is less than 2, then we simply return the input number as the square root of that number. Otherwise, we make a recursive call to my square root with twice right shifted number, and then we assign the return value to the square root variable. Then we left shift the square root value, and then we initialize the next integer square root variable with square root plus 1, and then we check whether the square of that next integer square root is less than or equal to the input number. If that is true, then we update the square root with the next integer square root. Otherwise, we do not update the square root variable. Then finally we return the square root as the square root of the input number. Let's move on to coding. First I rename the input parameter to number. Then I check the base case. If the number is less than 2, then I return the input number as the square root of that number. Otherwise, I call the my square root function recursively with the 1/4 of the value of the input number. I right shift the number twice, and then I multiply the return value by 2. I left shift the number once. Next I initialize the next integer square root variable with square root plus 1. Next I check whether the square of the next square root variable is less than or equal to the input number. If that is true, then I update the square root value with the next integer square root variable value, and finally I return the square root as the square root of the input number. Next I am going to run the test cases. All the tests passed. Next I am going to submit this program. Cool, this program is accepted. Next I am going to do the code walkthrough with sample input. The input number given is 9 and the square root of that 9 is 3. Okay, so first we check whether the input number is less than 2. So in this case number is 9. So we go ahead and make a recursive call after right shifting the number 9 twice. Okay, so then the frame 1 is created. Here the value of the number is 2. After right shifting 9 twice, we have number 2, and the square root and the next integer square root is initialized with 0. So here again we check whether the number is less than 2. In this case it is 2, but so we go ahead and make another recursive call after right shift the number twice. The number in the frame 2, we have the number with value 0, which is the base case. So we return that number back to the caller. Okay, so the control comes back to the frame 1. Okay, so here the square root returned is 0, and when we come back to the frame 1, the square root contains value 0, and left shifting the square root will be again 0. Okay, then we initialize the next integer square root variable with square root plus 1. So the next integer square root is 1. Then we check whether the square of the next integer square root is less than or equal to number. So we update the square root with the next integer square root. So the square root variable also will have value 1. Then the control will goes back to frame 0, where the input number is 9 and the return value of the my square root function will be 1 here, and we left shift that 1 by once, so the square root value become 2. Okay, Then we initialize the next integer square root with square root plus 1. So its value is 3. And then we check whether the square of that next integer square root is less than or equal to the input number. In this case, 3 times 3 is 9. So we update the square root variable with next integer square root's value. So it is set with value 3. And then finally we return that value as the square root of the number 9. That is an expected output. Next I'm going to do the time and space complexity analysis for this solution. The time complexity of this procedure is order of log n, where n is an input number. This my square root function is called recursively log n plus 1 times. Okay. Let's take a look at the case 1 where the input number is 1. So in this case my square root is called only once because the input value is less than 2. So the very first call itself we hit the base case. So my square root is called only once. And in the case of 2 the input number is 4. For this case the my square root is called twice. The first time it is called with value 4. Second time after right shifting this number it becomes 0 1. So the second call we hit the base condition. So we compute the square root by calling twice recursively. In the case of 3 the input number is 9, which is 1001. So in this case the my square root is called 3 times. First it is called with 9, then it is called with 2, and then it will be called again with value 0. So basically there are 3 times. So the number of times the my square root needs to be called is log n plus 1 times. So after removing the constant factor out, it is order of log n. So the time complexity is order of log n. The space complexity is also order of log n because when we use the recursive calls it uses the stack space. The maximum height of the call stack is log n. Okay, so that's why the space complexity is also order of log n. Thanks for watching this video. Have a great day.